Now, angular momentum, momentum, just momentum itself, as you are aware, is a measure of how much motion an object is undergoing. Linear momentum is a measure of the amount of motion which an object is undergoing when it is moving in a straight line. We have seen how to work out the linear momentum. Linear momentum P is equals to the mass of that particular object multiplied by the velocity. When an object is moving in a circle, or it's rotating about or spinning on its own axis.
Excuse sir.
Yes.
Some people are trying to log in, sir.
Yeah, but I can't see anything about them. There's just one person here, I'm saying. So I can't admit things which I've not seen.
Yeah. Alright, sir.
Yeah. So when we are talking about when an object is spinning on its own axis, then it has what's referred to as angular momentum. And as we have seen, angular momentum is a measure of how much rotational motion an object is undergoing. Now, just like there is something called conservation of linear momentum, there is also something called conservation of angular momentum. And these conservation things, these conservation laws or principles, they work on the same premises. For conservation to happen, it means that the momentum or the angular momentum before something happens must be equal to the angular momentum after a particular thing happens. That's what conservation means. That something should remain the same. Are we clear? For conservation to happen, it means that when you work out the angular momentum, and you have seen how to work out the angular momentum capital L is equals to the product of the moment of inertia I multiplied by the angular velocity. So when you work out the total angular momentum before an event happens, then you also work out the angular momentum after an event happens, then that angular momentum must be the same. That's what conservation of angular momentum entails here. Total angular momentum before event is equals to total angular momentum after event. Okay. Just like the other conservation law we looked at, principle we looked at, conservation of linear momentum, there should be no external torque in this case, which acts on an object. The reason why we are saying is that there should be no torque applied on an object is because you have seen what torque does. When you apply a torque, here equation number 24, if there is a torque present, equation number 24, torque is equals to moment of inertia, which is what this particular object has, multiplied by angular acceleration. So if there is a torque present, this torque present is going to show itself in terms of acceleration. When there is acceleration, angular acceleration, it basically means that the amount of angular motion is going to increase. There's going to be an increase in angular motion. If there's going to be an increase in angular motion, then there can be no conservation. Are we clear? Torque causes angular acceleration. Torque is equals to moment of inertia multiplied by angular acceleration. So if there is a torque present, this torque is going to cause angular acceleration. Basically, there's going to be an increase in the angular velocity of this particular object, or it's going to be a reduction in an angular velocity of this particular object. If there is an increase or a reduction, basically what we are saying that there's going to be an angular impulse. So this particular object is going to gain motion or is going to lose motion. If there is a gain or loss of motion, then there can be no conservation, which is going to happen. Are we clear? So for conservation to happen, for conservation of angular momentum to happen, there should be no external torque acting or on the rotating or spinning objects. Only when the torque is equals to 0 is there going to be conservation of angular momentum. Are we clear? That's the first thing you're supposed to be aware of. We can only have conservation if there is no torque. If at that particular point there is no external torque applied on this particular object which is rotating or spinning, then you can have conservation. If you have a torque, then that torque is going to cause your object to spin faster or your object to slow down, and when that happens, you end up either with a gain in angular momentum or is the loss in angular momentum, and when that gain or loss happens, you cannot have conservation. Are we clear? Is this requirement clear to everyone? Okay, so if it's very clear, then we can move forward. So with conservation of angular momentum, basically we are interested in certain events like a coupling. When you couple spinning disks, or as we are going to see, when a star collapses on itself, when something which is bigger becomes smaller, it tends to spin faster. Even if there is no torque which has been applied. When you have got an object which is spinning, when a big object is spinning, then this big object becomes smaller, it will tend to spin faster. When it collapses itself, it tends to spin faster. Okay, so let us have a look at a few examples pertaining to this conservation of angular momentum. Okay, so here we have got an example of rotating disks. This is the first disk, disk 1 at the bottom here. Disk 1 has got, it's a disk, so it's rotating, it has got a mass. If it has got a mass, as you have seen, then it has got moment of inertia. So disk 1 has got moment of inertia I, and it is rotating with angular velocity omega. Disk 2 is being dropped onto disk 1. So initially disk 1 is rotating with omega, disk 2 is not. So since disk 2 is not rotating in any way, it does not have any velocity, angular velocity, therefore there is no angular momentum associated with it. So we can work out what the momentum is before this disk 2 couples or rests on disk 1 so that they rotate together. So this is what is referred to as a coupling. When you kind of like join, you put together rotating things, objects, then you couple them. So in this case, you have got your first disk 1 is rotating with omega I, disk 2 is not rotating at all. So before the coupling and after the coupling, make sure that there's no force, there is no torque present, then you can work out what the moment of inertia is going to be. So in this case, this is an example basically meant to show some So what do we have here? What have I written? So a disk of moment of inertia I is rotating freely with angular velocity omega 1. Okay. When a second non-rotating disk of moment of inertia I2 is dropped on it as shown in figure 4, the two then rotate as a unit. Find the final angular speed omega f, which is the speed of the disks after they have been coupled together. So in this case, there is a requirement that no torque be applied on the disks. If there is no torque applied on the disk, as we can see, there is no torque present, then the total angular momentum before and after coupling must be the same. So before the coupling, only disk 1 is rotating with angular velocity omega 1, and disk 2 in this case is non-rotating. Therefore with disk 2, the the angular velocity is 0 meters per second. So here it says we obtain this expression. Now with this expression, I think this thing was supposed to be written the other way around. I'm not sure exactly. With this bit here, what we have here, moment of inertia 1 multiplied by omega 1 here. This is the total angular momentum before coupling. So the angular momentum is due to only the first disk with its moment of inertia, and it's multiplied by, so this one here, omega 1, I1 multiplied by omega 1. So that's what gives us a moment of inertia. Since this other one is not rotating, it's non-rotating, when you multiply whatever the moment of inertia is of this guy times whatever the angular frequency is, or the angular velocity, which is 0, you get nothing. So what you have this side, this side is your moment, the total angular momentum before coupling. Then what you have this side is the total angular momentum after coupling. However, when this thing couples, so here you have got whatever the moment of inertia is. This thing was not properly, I think this thing was not written properly. I didn't write this properly. So it's very confusing because it looks like this one here and these are the same. But this is supposed to be for our velocity, the angular velocities of the disks after the coupling. So in our case, so we have I think I was supposed to write omega f1 or something like that. Okay, so here we have got our moment of inertia for the first disk multiplied by the moment of inertia of the second disk after coupling, plus the moment of inertia of the second disk multiplied by the moment angular velocity of the second disk after coupling. So this bit I think needs to be rewritten so that it looks much better than it is. Then if these things are going to rotate after the coupling has happened, they will rotate with the same velocity, angular velocity. So that's probably why we are saying here omega 1, this bit here, and this is after the coupling are going to be the same. So we end up having omega f things are going to be rotating with the same angular velocity. Then you can factor out the omega f, since the omega f is going to be the same, so you end up with I1 plus I2 equals to omega f. So this is our, basically this is an expression for our total angular momentum after coupling. So this bit here, which I've written omega 1 and omega 2, I think this is supposed to be written as omega 1f or omega 2f here. I think I should have done that, omega 1f and omega 2f. I think that's what I should have done. So that's just since the coupling happens, so they spin at the same velocity, so you end up having just omega f, which is the velocity with which the first disk is coupling is rotating, is the same as the velocity with which the second disk is rotating. So we end up with this expression here. So I1 plus I2 equal in brackets multiplied by omega f, which is your final angular velocity. So since we are talking conservation, so this bit here, which is our linear momentum before coupling happened, which is what you have this side, linear momentum before coupling should be equals to the linear momentum after coupling. What we are saying here is that the amount of motion which is there before the coupling happens should be the same as the amount of motion which is there after the coupling happens. Is that clear? The same thing applies, like what we are doing with conservation of conservation of linear momentum. The same thing is what we're doing here with conservation of angular momentum. So we are saying that the amount of motion before and after should be the same. Are we clear?
Yes, sir.
Okay. So next, since we are looking for the final velocity, angular velocity of the disks, so we rewrite our expression like this. Then we try to divide both sides by this term, I1 plus I2. We divide both sides by the term I1 plus I2. When we do that, what do we end up with? So we end up with, so we end up with the following expression. We end up with this expression here. I1 multiplied by omega 1 divided by I1 plus I2. This expression is basically just going to result in a reduction of whatever the velocity was, because you can factor out this thing. So you're going to end up with I1 divided by I1 plus I2 multiplied by whatever this is. So this I1 divided by I1 plus I2, this is going to be this I1 divided by I1 plus I2, this is going to be less than 1. So whatever this fraction is, I1 divided by I1 plus I2, which is less than 1, multiplied by this term here, you are going to end up with an expression of velocity which is going to give you a final velocity which is basically less than the initial velocity. So it's going to slow down. Basically what we are saying is here is that when you have a setup like this, from applying conservation of linear angular momentum, when you've got a setup like this, when this thing couples, it's going to slow down. That's basically what we're saying. Are we clear? I'll need to redo or rewrite this example. It doesn't look very nice, especially I'm not happy with what is the way I've written it here and how I do this. So I need to rewrite this part here. I also need to write this part here just after the class. Then I can re-upload the notes. Then you can have a look. Okay. So that is about coupling. The other example which we have is where you have a star which is spinning. Then this star collapses on itself. Okay. So basically it becomes smaller. But when you've got a big thing spinning, then it collapses on itself, so that's with a smaller size, something else tends to happen. So example number 16, a neutron star is formed when an object such as a neutron star is formed when an object such as the sun collapses on itself. The sun is a massive burning ball of hydrogen and helium. Suppose a uniform spherical star of mass m and radius r collapses into a neutron star of radius 10 to the power minus 5 r. So basically it collapses so that it becomes something which is very, very small, about 10,000 times smaller than what it is. Okay. If the original star had a rotation speed of 1 revolution every 25 days, as our sun does, what will be the rotating speed of the neutron star in radians per second and revolutions per second? So in this case, of course, there is no torque being applied on this particular star which is about to collapse. So if there's no torque being applied, then we can say that there's going to be conservation of angular momentum. So the total angular momentum of the star before it collapses and after it collapses should be the same. So in this case, since there's only one object which is rotating, then it collapses on itself, we can say that the initial moment of inertia multiplied by how fast the star is rotating, angular velocity omega I is equals to the final moment of inertia multiplied by our angular velocity of the star, the final angular velocity, where omega I and omega w are the moment of inertia and angular velocity of the original star before collapse, and omega f and omega I are the moment of inertia of the star after the neutron star after collapse. Now we know that if something is like a star which is spherical, in this case, for such an object we can always work out what the moment of inertia is. For anything which is spherical, the moment of inertia omega I is going to be equals to 2 over 5 mr squared. Okay, then for a neutron star, we are told the neutron star has got a radius which is equals to this much, 10 to the power minus 5 r. So for a star, for our star, this is the moment of inertia. For the neutron star, it is also still spherical, but it is a much smaller sphere. So in that case, our final moment of inertia omega f if is going to be 2 over 5 m. Then our radius, which is 10 to the power minus 5 r, the whole thing squared. When you do this, when you square this whole thing, you end up with this bit. You end up with this moment of inertia is equals to 10 to the power minus 10. Then this term remains. So this bit here, 10 to the power 5 squared gives you this 10 to the power minus 10. Then the remaining part is the r. R is going to be squared. So when you square the r, then you put it together with this 2 over 5 m r squared. You end up with this bit here, 2 over 5 m r squared. But the 2 over 5 m r squared which you have here is what you have here, 2 over 5 m r squared. So basically what we have done is we have expressed the moment of inertia of our neutron star, our collapsed star, in terms of the moment of inertia of the original star. So final moment of inertia is going to be 10 to the power minus 10, then 2 over 5 mr squared, which is just equals to moment of inertia final if is equals to 10 to the power 10 the moment multiplied by II, which is the moment of inertia of the star. Is this clear on how we have expressed our moment of inertias?
Yes, sir.
Okay, so we know how much the moment of inertia of the original star is. We know what the moment of inertia of the neutron star is after collapse. The only other thing which means we know this bit. We know this bit, this one here. We know this one here. Okay. The other thing we know is we have been told how fast the star is rotating before it collapses. 1 revolution every 25 days. We know a revolution in angular displacement is 2 pi radians, but the amount of time it takes in this case is 25 days. So the original star has got an angular velocity of 1 revolution every 25 days. So we need to express the time in seconds. This 25 days has to be expressed in seconds. So 25 days in this case, t is equal to 25 days. That's going to be 25 days multiplied by 24 hours divided by per day. So when we do this, the day is going to cancel out with this. So we have 25 times 24 hours, but our interest is to express this whole thing in seconds. So you've got this 24 hours, then you express it 60 minutes multiplied by an hour. So this hour is going to cancel out this hour here. Then you've got 60 multiplied by 60 seconds divided by a minute. Then this minute is going to cancel out this bit here. So you've got this day cancelling out this. Then you've got the hour cancelling out this here. Then you've got the minute cancelling out what you have here. So at the end of the day, basically what we have, 25 days expressed in seconds is just 25 times 24 times 60 times 60, and that gives us 2,160,000 seconds. Is this clear? So this is how much time in seconds passes. Is that clear to everyone?
Yes, sir.
How you make the conversion from days to seconds. So since this is how much time has passed, and we know 1 revolution is equals to 2 pi radians, we can find out what omega I is. What is the original angular velocity of our star? So in this case, when we do that, so we can find out how much is I, omega I. So omega I is going to be equals to theta, which is our angular displacement divided by the time. So that's going to be, omega I is going to be 2 pi radians, since that's 1 revolution, divided by the time in seconds. So we end up having omega I equals to 2.91 times 10 to the power minus 6 radians per second. So this is how much the angular velocity is in radians per second. Very, very small. If you want, you can change this angular velocity in radians per second. You can change it to revolutions per second. So in this case, you're going to end up having 2.91 times 10 to the power 6 radians per second multiplied by 1 revolution divided by 2 pi radians. So you end up with 4.6 times 10 to the power minus 7 revolutions per second. So this is still very, very small. Per second, how many revolutions are happening? So with that information, now try to work out, we try to enforce conservation of angular momentum. So we know our moment of inertia is I, our angular velocity is what we have found here in radians per second. This is what you found there, put there, equals to our final moment of inertia. That's going to be 10 to the power 10 II, moment of inertia in terms of the moment of inertia of the original star multiplied by the moment of angular velocity of the neutron star, which is what you have here. We have I appearing this side. We've got I, which is here, so we can cancel out those i's. So we're going to remain with only this term here. We're going to remain with this, then this, and that. So we're going to remain with 2.91 times 10 to the power minus 6 radians per second equals to 10 to the power minus 10 multiplied by omega f. So if we divide both sides by this bit here, then you're going to end up with omega f is equals to 2.91 times 10 to the power minus 6 radians per second divided by 10 to the power 10. Then when you do this, you're going to end up with omega f is equals to 29,100 radians per second. So this is going to be your final angular velocity of the neutron star. So what you're seeing is that when something which is big collapses, compare this, your final velocity of the same object, to what the initial velocity was, which is this, which is here. So you're seeing that this particular object spins faster. So when something collapses on itself, when something becomes smaller, when something which is big with a large value of moment of inertia is rotating, then suddenly it becomes much, much smaller. It tends to spin faster. I don't know if you people have been watching. Have you been watching Olympics? Or it's the Winter Olympics where you've got those ladies with who spin on ice skating, who do ice skating. Have you ever seen them?
Yes, sir.
Yes. So you notice when those guys when they extend their hands out, they spin much slower. But when they bring their hands close to the chest, they spin faster. The reason is this: it's just because what's happening is conservation of angular momentum. So in this case, our neutron star has got this amount of angular velocity. Now, what is it? You can also try to express this angular velocity in terms of revolutions per second. So that's going to be 29,100 radians per second multiplied by 1 revolution divided by 2 pi radian. So you're going to end up with 4,631 revolutions per second. So you can see in terms of revolutions per second, this is what you have after the star has collapsed. Then before that, this is what you had. So it was rotating very slowly as a star, just like our star rotates very slowly. We have been told that from that question, It takes our star 25 days to spin on its axis once. 25 days to spin on its axis once. So that's how slow things are. Then the day our star is going to collapse, probably in the future, as all stars do, it will start spinning faster. Now what we want to do is we want to compare, another thing we want to show is we want to compare our final angular velocity with our initial angular velocity. When you do a comparison of our final angular velocity with our initial angular velocity, you see our omega f divided by omega I, so that's going to be, this is 29,100 radians per second divided by 2.91 times 10 to the power -3 radians per second. When you do this division, you're going to end up with this. Omega f divided by omega I is equal to 1 times 10 to the power 10. This is just basically a fancy way of writing this. Omega f is equal to 10 times 10 to the power 9 omega I. This is 10 billion. So you see that your neutron star is going to rotate 10 billion times faster than the original star. And this is exactly what you see with those ice skating ladies. So what I'm going to do is I'll stop recording because I want to go to YouTube. I'll